A black rock chimney expels thick smoke over the Pacific sediment. How does life thrive where the sun never touches and the water boils? We will observe the moment when deep geology rewrote the rules of terrestrial biology. In February of 1977, the Alvin submersible descended 2,500 meters deep. The expedition's target was the Galapagos Rift, an active fracture in the oceanic crust located in the eastern Pacific Ocean. The 18-ton bathyscaphe slowly sank through the pelagic zones. Geologists on board expected to find only barren basalt fields. At this depth, darkness is absolute, and the pressure from the water column crushes any empty space. The scientific theory of that decade stated that oceanic biomass gradually decreased with distance from the surface. Without light to sustain phytoplankton, the sea floor should have been a rocky desert, occasionally punctuated by sinking whale carcasses. But the vehicle's external sensors registered an anomalous thermal spike. The water around the titanium hull began to gradually warm. The pilot maneuvered the heavy submarine against the current and adjusted the quartz spotlights, revealing a mineral structure that should not have existed in that quadrant of the ocean. The mineral structure, illuminated by the spotlights, housed a dense field of white shells upon the volcanic rock. The expedition, funded by the Woods Hole Oceanographic Institution, wasn't searching for biology. Scientists Robert Ballard and Jack Corliss were mapping the seafloor with acoustic instruments, seeking heat sources. The premise of the mission was strictly geological. Until that year, the global biological consensus was rigid and unquestionable. All life on Earth depended ultimately on photosynthesis. The sun fed the plants and algae, which fed the herbivores, sustaining the entire trophic chain up to the great predators. Where light failed, energy ceased. The abyssal ecosystem relied solely on marine snow, the organic remains and detritus that slowly drifted down from the productive surface to the muddy seabed. The Alvin hovered over the newly formed volcanic vent. The typical oceanic water temperature in that abyssal zone is a harsh 2 degrees Celsius, but the submersible's external thermometer read 17 degrees and continued to climb as the robotic arm approached the dark fissure. The heat emanated from narrow fissures in the newly formed basalt. Seawater penetrated the fractures in the Earth's crust, heated violently in the subterranean magma, and returned to the ocean laden with dissolved minerals. And around these thermal vents, at the boundary between the cold crust and the hot fluid, researchers observed an impossible biological oasis. The abyssal oasis teemed with organisms that science had never catalogued. Anchored directly to the basalt, giant tube worms swayed with the invisible thermal current. They measured over 2 meters in length, imposing structures with calcareous white tubes and bright red plumes at their upper ends. Beside them, blind crabs walked slowly over rocks covered by dense mats of filamentous bacteria. Clams the size of dinner plates clustered in the deeper crevices, filtering the murky fluid. The density of life in that small stretch of seafloor rivaled that of a tropical rainforest on the planet's surface. All of this occurring under extreme physical conditions. 2,500 meters beneath the waves, the pressure exceeds 250 atmospheres. It's a mechanical force sufficient to compress a solid block of wood and expel all the air from its fibers. Beyond the crushing pressure, the chemical environment was lethal. The hot fluid gushing from the chimneys was saturated with hydrogen sulfide, a sulfur-smelling gas highly toxic to the overwhelming majority of marine animals.
Exposure to this concentration of sulfide would paralyze the cellular respiration of a pelagic fish in mere minutes. The survival of that benthic flora demanded unprecedented biological machinery. But the biological machinery needed to contend with a problem greater than water toxicity. Subsequent expeditions mapped even more extreme sources along the mid-Atlantic ridge and the Pacific Ring of Fire. These larger geological formations, composed of precipitated metallic sulfides, became known as black smokers. In these locations, mineral chimneys grow dozens of meters above the ocean floor. The expelled water reaches temperatures far beyond the boiling point on the Earth's surface. The probe's thermometers registered 400 degrees Celsius. The volcanic fluid only avoids immediate vaporization because the weight of the 3-kilometer water column keeps it compressed in a liquid state. It's an environment of concentrated infernal heat surrounded by near-freezing waters. Without starlight, what is the invisible engine that fuels this biomass? The answer wasn't in the geology of the vents, but hidden within the internal tissue of those red and white creatures. Marine biologists who dissected the first tube worm specimens noticed a disturbing anatomical anomaly. Adult animals possessed no mouth. They had no stomach, no intestine, nor any trace of a functional digestive system. They didn't hunt microorganisms. They didn't filter detritus from the water column. The interior of their bodies was filled with a spongy, vascularized organ, the trophosome. And within this dark organ, microscopes revealed billions of microorganisms working in synchrony. The synchronized microorganisms operated like chemical refineries in absolute darkness. Laboratory analysis revealed a metabolic process that shook the foundations of biology. The process was christened chemosynthesis. Instead of using the sun's photons to generate energy, these extremophile bacteria utilize the chemical bonds of minerals. They actively absorb the toxic hydrogen sulfide expelled by the volcanic chimneys. Through oxidation reactions, they break down the gas molecules and use the released energy to fix carbon from the seawater. The bacteria literally manufacture food from dissolved rock and pure poison. The relationship with the giant tube worms is an example of perfect and obligatory symbiosis. The worm provides a safe haven against marine currents and captures chemical compounds from the water with its red plume. The plume is rich in specialized hemoglobin, adapted to transport oxygen and sulfide through the blood without poisoning the tissues. In exchange for the reagents delivered within its interior, the bacteria feed the host from the inside. They provide all the necessary nutrition for the worm to grow at astonishing rates on the sea floor. The entire food web around the chimneys depends on this productive base of this microbial process. It's a self-sufficient ecosystem, entirely disconnected from the planet's surface. If the sun were to extinguish tomorrow and the Earth's surface froze, life in the hydrothermal vents would continue to thrive on the Pacific floor, completely oblivious to the cosmic collapse above. This ability to ignore the surface answered the central question left by the Alvin expedition. Life thrives where the water boils because it doesn't need the star that illuminates Earth. It uses the planet's own internal heat and violent volcanic chemistry as its primordial fuel. Hydrothermal vents prove that biology is not a hostage of sunlight. It builds entire food chains from the fractures in the Earth's crust, shaping life in absolute darkness. The discovery suggests that subterranean oceans on distant moons may harbor the same oases. Earth's ocean harbors geographical boundaries defined precisely by this absence of luminous energy. 1,000 meters deep, the last blue photons fail in the water column.
It is the physical limit of the bathopelagic zone, where eternal darkness begins.